All right, you're welcome. So this week's lecture. So today we'll talk about nuclear structure. In the last lecture, we talked about the structure of the atom, and we start from there today. According to Rutherford's interpretation of the experiment by Geiger and Marsden, so we said that the atom, is made up of a nucleus. Okay, so this is a nucleus, and that there are electrons revolving around the nucleus. And of course, we talked about some of the limitations of the Rutherford's interpretation of the structure of the atom. Anyway, so today we are interested in the nucleus. So in the nucleus, there are protons and neutrons. So the protons and the neutrons, they reside in the nucleus, and both of them are referred to as nucleons. Okay, nucleons. So when you hear the word nucleon, so it's referring to either proton or the neutron. Now, there are some terminologies that we need to define before we move on, like the atomic number of a nucleus. So the atomic number of a nucleus is the number of protons. So this is the number of protons in the nucleus. So the protons are positively charged, neutrons are neutral. So in the structure of the atom, the electrons are negatively charged. So the number of protons that you have in the nucleus is called the atomic number, and it is often denoted as Z. So that is the atomic number. So the same way, the neutron number is the number of neutrons. So neutron number. So this is the number of neutrons in the nucleus. So that is the neutron number, and it is often denoted as N. Then we have the mass number, which we denote by A, so capital letter A. So this is the sum of the protons and the neutron number. So the sum of protons and neutrons in the nucleus. So we denote this by A. So this A is actually the sum of the atomic number and the neutron number. So A is Z plus N. So if you are given the mass number of a particular nucleus, then you can determine the neutron number. For example, if you are given oxygen 20, so which is written like this. So if you want to write a nuclide, okay, so let's say the nuclide is the nuclide X. So we put the mass number here, the atomic number here, and the neutron number here. Okay, but this is not often used. So in most cases, we do not write the neutron number, because we believe that if you are given the mass number and atomic number, you can easily determine the neutron number, because the neutron number will be the mass number minus the atomic number. In fact, in research, the Z is also not often written. So we just write A, okay, like oxygen 20. So we know that oxygen, the atomic number for oxygen is 8. Okay, it's 8. So we do not write the 8. So we only write the mass number, because this mass number can change. We can have oxygen 16, oxygen 17, 18, 20, 22, and so on. Okay, so that is why we must specify the mass number of the oxygen isotope we are talking about. So that's that. So this oxygen 20, so it means Z is 8. This should be well known, and the mass number is 20. So in this case, the neutron number will be A minus Z, which is 20 minus 8, and that will be 12. Okay, so we can write the full form of the isotope as 12. So 12 plus 8 will give what? 20. So next, this will lead us to the definition of isotopes. What do we mean by isotopes? So isotopes. Okay, so isotopes, these are nuclides. So these are nuclides. So when we say nuclides, that is a nucleus with a specific mass number. So these are nuclides that have the same atomic number, nuclides with the same atomic number but different mass number, Okay, and what are the examples? The examples are many. For example, so let me put the examples here. So examples: 1, we can have oxygen 16, oxygen 18, oxygen 20, oxygen 22. So these are nuclides, or the isotopes of oxygen. We can have calcium 40, calcium 44, calcium 48, and so on. These are isotopes of calcium. Isotopes of calcium. And these are isotopes of oxygen. Okay, then the most common isotopes, the hydrogen isotopes. So you have the deuterium 2,1 and the tritium 3,1. So these are isotopes of hydrogen, so on and so forth. So that's the first definition, isotopes. So these are nuclides that have the same atomic number. So because the atomic number of this calcium is 20, of this calcium is 20, of this calcium is 20, of this hydrogen is 1, 1, 1. Oxygen 8, 8, 8, and so on. But the mass number differs. The next, isobars. So isobars, these are nuclides that have the same mass number but they have different atomic number. So these are nuclides with the same mass number but different atomic number. Okay, they have the same mass number. And what are the examples? So a simple example is calcium 40, which is 20, and potassium 40, where Z is 19. So Z here is 20, Z here is 19. A here is 40, A here is 40. So they have the same mass number, which is 40. Then the next definition is isotones. So these are nuclides. With the same neutron number, but different atomic number. So they have the same neutron number but they have different atomic numbers. So what are the examples? We can also use the calcium isotopes 40, calcium 40, as well as potassium 39. So this calcium 20, the Z atomic number is 20. So the neutron number will be 40 minus 20, which is 20. The potassium, the atomic number is 19. So 39 minus 19 is 20. So they have the same neutron number, which is 20. So N equals 20. In this case, A equals 40. Okay, so these are isotones. Now, if we want to represent the mass of nuclides, nuclides are very, 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 very small, and we know that the SI unit of mass is kilogram, but to measure the masses of nuclei, we use what we call the atomic mass unit. So the symbol can be AMU, or U, AMU or U. So if you see U or AMU, so it means atomic mass unit. So and one atomic mass unit in SI units, if you convert to kilogram, so it's approximately 1.66057 times 10 raised by minus 27 kilogram. So that is the conversion of the atomic mass unit to kilogram. So you can see it's very, very small. Times 10 raised by minus 27, very, very small. Okay, so the mass of a proton, for example, the proton, the mass is 1.007276 U. Okay, so if you convert this to kilogram, it should be around 1.67262262 times 10 raised by minus 27 kilogram. So it's a very, very small mass. Okay, now next we'll move to nuclear stability and binding energy. Nuclear stability and binding energy. Okay, now we stated earlier that the proton is positively charged. Okay, let me write in full. Positively charged, and the electron is negatively charged. Well, we're talking about the nucleus now. So the neutron has no charge, it's neutral. Okay, now the force, and this proton and neutron, so let me draw let's say nucleus, and these are protons, the blue ones, and let's say the red ones are neutrons. Okay, the red ones are neutrons, the blue ones are protons. So the blue ones are positively charged, while the red ones are negatively charged. So there will be a Coulomb force of repulsion between the protons. Okay, these blue ones, they are the protons, so proton, and the red is neutron. Now, so there should be a Coulomb force of repulsion between two protons, because if this proton is positively charged and this proton is positively charged, so there should be a force of repulsion between the two. The same thing with this third proton. So, but if that happens, if they all repel, if the protons repel, then it means there will be no proton in the nucleus, and we will not have what we call a nucleus now, and invariably an atom. So, but what happens is that there is, and that Coulomb force does not affect the neutron, because the neutron has no charge. You know, the Coulomb force depends on the charge of the first object, the charge of the second object, and the distance between the two. Okay, so now since this neutron has no charge, so there is no Coulomb force affecting the neutron. Now, but the reason why we have a nucleus and the protons are not scattered is because there's another force that holds the proton together. We call that force the nuclear force. The nuclear force. So it is the force that holds the protons and the neutrons together. So it is not a force that is just for charged particles. No, it is a force that affects the nucleons. The nucleons, you know, the nucleons, that is proton and neutron. So this nuclear force affects the proton and the neutron in the nucleus. And the nuclear force has a short range. Okay, it has a short range, like the size of the nucleus. So when this separation between two nucleons is above a certain value, okay, then the nuclear force will not have any effect again. So the nuclear force is like this. So let's say so let's say this is the separation between the two objects, and this is the gravitational potential, the interaction potential between, not gravitational, the potential, the interaction between the two nucleons. So it starts with, so this is the positive side and this is the negative side. So the graph, the shape of the graph is something like this. Okay, so at a certain point the interaction is attractive. Okay, this point, within this point, is attractive. But when the when two nucleons approach each other and they try to collide, so before they collide, that nuclear force will turn to a repulsive force, so that the two nucleons will repel. Then at huge distance, at large separation distance between two nucleons, the interaction potential tends to 0. Okay, it tends to 0. So, and that is the shape of the interaction potential between the nucleons. Now, so this nuclear force holds the nucleons together in the nucleus. So what if we want to separate these nucleons? We want to separate these 6 nucleons in the nucleus. Now we need to supply certain energy, and that energy is equivalent to the binding energy. That is the energy that holds the nucleons together. So the binding energy of a nucleus, is the energy required to completely separate the protons, or the nucleons actually, the protons and neutrons, of which it is composed of. Okay, so that is the binding energy. Now, so it means if we have helium-4, for example, helium-4, the atomic number of helium-4 is 2, the mass number is 4, therefore the neutron number n is going to be what? It's going to be 2. So if we measure the mass of the atomic number and we measure the mass of the mass of the protons, okay, if we measure the mass of the protons, let's call that mh, and we measure the mass of the neutrons, because in helium-4 you have 2 protons and 2 neutrons. In helium-4, 2 protons and 2 neutrons. Okay, so if you measure the mass of the protons, or let's say the mass of a proton is mh, so that if you want to consider the 2 protons to be 2 multiplied by mh, and the mass of neutron is mn, okay, mn, mass of the neutron. If you add the mass of the proton, which is 2 times mass of proton plus 2 times mass of neutron, and you subtract the mass of helium-4 itself, okay, this value does not equal to 0. We expect that since helium-4 is made up of 2 protons and 2 neutrons, that the mass of the 2 protons and the mass of the 2 neutrons should be equal to the mass of helium-4, but we do not get this. Okay, what we get is that there is a non-zero mass. Okay, so if you subtract helium-4, so we get what we call the mass defect. So that difference in mass is what we call mass defects. Okay, mass defect. That's the difference between the masses of the nucleus and the mass of the particular nucleus or nuclide. So that difference in mass is what we call mass defect. And from this mass defect, one can obtain the binding energy. That is from Einstein's energy relation. So the binding energy is the mass defect multiplied by c squared. Note that the formula to finally obtain the binding energy formula is the atomic number of particular nucleus. In this, for helium-4 it is 2, multiplied by the mass of hydrogen plus the neutron number multiplied by mass of neutron, then minus the mass of the nucleus X. Then we'll multiply this by c squared. So let me call this equation 1. Now this mh is mass of hydrogen, and hydrogen atom has electron in it. So the mass of the electron here, so in practice this is what we often use. We neglect the mass of the electron. Okay, so in practice, you may be given the mass of the nuclide. Okay, then of course from there you can determine the mass of the number of neutrons and the number of protons. So then you now multiply Z by the mass of hydrogen and the neutron number by mass of neutron, and so on. Okay, so this formula should it's a formula that you should be strongly familiar with. So I label this as equation 1. Now, but we know that the masses of this hydrogen, of the neutron number of the particular nucleus, are in atomic mass unit U. So what we do is we convert that U to MeV, because the unit of energy will be in MeV. So if these masses are in atomic mass unit, then we'll convert them to 1 U is approximately 931.49. So MeV per c squared. MeV per c squared. So that this formula, equation 1, can be written as ZmH plus NMN minus Mx, all masses in atomic unit, then multiplied by 931.49 MeV per c squared. But this square will cancel this c squared. Okay, so that at the end of the day you just have MeV. Then we can also be asked to calculate the binding energy per nucleon. So the binding energy per nucleon is, so just take the binding energy, then divided by the mass number. The binding energy divided by the mass number. So that is the binding energy per nucleon. So let's take an example. So example 1 for today. So the example is calculate the binding energy and binding energy per nucleon, binding energy per nucleon for 2 helium, that's helium 4. Now you are given the mass of hydrogen to be 1.007825 U, mass of neutron to be 1.008665 U, and mass of the nucleus, helium 4, is 4.002603 U. Now, so solution. So this is a straightforward question. So the binding energy, that's the first case, the binding energy is Z mass of hydrogen plus N mass of neutron, then minus the mass of helium 4 in this case, then multiplied by 931.49 MeV. So that this will be Z. Now for this helium 4, Z is 2, A is 4, then N is 4 minus 2, which is also 2. So Z is 2 multiplied by MH, which is 1.007825 U, plus N is 2 multiplied by 1.008665 U, minus mass of helium 4, which is 4.002603 U, then multiplied by 931.49 MeV. So if you do the arithmetic, you obtain 0.030377 U, then multiplied by okay, so we can remove the U. Okay, so multiply by 931.49 MeV, because we said 1 U is 931 what is it? 1 U is 931.49 MeV per c squared. So if you remove the M, so it means here should be multiplied by c squared. Same thing here. Okay, so it should be multiplied by c squared. The same thing here. So that in this case it will be so the u will be present. So let me do it systematically. So in this case u will be present, then c squared. So c squared. Then since we said 1u is 931, so it will be 0.03077. so 1u is 931.49 MeV per c squared with this c squared, so that this c squared will cancel c squared, and if you multiply the two values you obtain that the binding energy is 28.2961755 blah 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 MeV. So your answer, this c square will cancel this c square, so your answer will be only in MeV. Now what about the second part? Second part says that we should calculate the binding energy per nucleon. So it will be this value, 28.2961755 MeV, divided by A, which is the mass number. The mass number of the nuclide here is 4, helium-4. Okay, so the mass number is divided by is 4, and if you do the division, so you obtain approximately 7.07 MeV, so per nucleon. So that is about that. Next is about radioactivity. So radioactivity, I think, let me use a new page for radioactivity. Radioactivity. So radioactivity is the disintegration of an unstable nucleus to a more stable nucleus with the emission of some particles like alpha particle, beta particle, or gamma radiation. So when an unstable nucleus emits any of these particles, so for example alpha particle, so it can emit alpha particle, it can emit a beta particle, it can also emit gamma ray. Okay, so if it emits alpha particle, so we'll talk about this properly later, but alpha particle is a helium nucleus, so the nucleus is the same thing as the nucleus of helium-4, while beta particle is an electron. Okay, electron, and gamma ray, they are just photons. So the charges on the electric charges on helium-4, because here you have 2 protons and 2 neutrons, so it's plus 2e. Then on this is minus e, and why this there's no charge. We'll talk about this later. But when an unstable nucleus undergoes radioactive decay, the rate at which that nucleus will decay, okay, the NDT, the rate of decay, is proportional to the actual number of atoms, actual number of nuclei that are present at particular time t. So if you remove proportionality sign and we introduce a constant, we have that the NDT is what? Is minus lambda, actually, n. Why do we have a negative sign here? So the proportionality sign here is lambda, so we call lambda the decay constant. The decay constant. So why do we have a negative value? So we have a negative value here because over time the material will decrease in size, will reduce in size over time. Okay, so if the number of atoms present at time t equals 0, if they are n naught, and at time t equals, maybe at time t which is greater than 0 is n, so this n will be less than n naught, so the material will continue to reduce in size. So that's why we have a negative sign here. So let's say at time t equals 0, at time t equals 0, the number of atoms present, number of nuclei at time t equals 0, we denote it as n naught, and at time t, okay, at time t which is greater than 0, okay, and we denote the number of nuclei present or remaining as n. Okay, then from this dn dt, we said the rate of decay is proportional to is proportional to n, the number of nuclei present. So if we rearrange this so that we have dn over n equals minus lambda dt, so that we're able to integrate this with respect to n and integrate this with respect to t. And we said the original time t naught, t is 0, and the final time is t. So the original number of nuclei present is n naught, and the number of nuclei present at time t is n. So we have to work out the integration. So if we integrate this, we have ln n, natural logarithm of n, and the limit of integration from n naught to n. The same thing here, we have minus lambda t from 0 to t. Now, so this can be written as ln n minus ln n naught equals minus lambda t, because here it should be minus lambda into bracket t minus 0. Okay, so t minus 0 is still what? Is still t. And we can write this as ln n over n naught equals minus lambda t. Then we can take the exponential. So we take exponential of both sides, so that we have exponential ln n over n naught equals exponential minus lambda t. So when you take exponential of the log of a number, you get the number. So if you take exponential ln 2, the answer will be 2. Exponential ln 20, the answer will be what? 20, and so on and so forth. So if you, okay, we have done this now. So exponential ln n over n naught is going to be what? N over n naught, so equals exponential minus lambda t. And this implies that n equals n naught exponential minus lambda t. So this is the number of nuclei that will be present at time t, which is greater than 0. Okay, let me label this as equation 4. I think the last equation I labeled was equation 3. So let me label this as equation 4. So this formula is a very, very useful formula, that the number of nuclei present at time t equals n naught, which is number of nuclei at time t naught. So the lambda is called the decay constant, as I explained before, and it is defined as, so the decay constant lambda, so is defined as the probability of a decay per nucleus per second. Okay, now this will lead us to activity. So when we started with the rate of decay, we said the rate of decay is minus lambda n. So this activity is actually the product of, so activity R, let me use R, is actually the modulus of the rate of decay. Okay, rate of decay. And if we define this equation 4 by, if we differentiate equation 4 with respect to t, that is, this is equation 4, we differentiate with respect to t, this will be minus lambda n naught exponential minus lambda t. That's what we have. Since we are saying we are taking the modulus, then this will be lambda n naught exponential minus lambda t. That is, the activity R is lambda n naught exponential minus lambda t. Let me call this equation 5. Right? I think, yeah, the last equation was equation 4. Now this lambda n naught is the activity at time t equals 0, or at time t naught, the initial time. Okay, so R naught is lambda n naught, so that we can write our R as R naught exponential minus lambda t. So this is an expression which is similar to equation 4. for the number of nuclei present. So this is activity. Okay, now the next definition, the next term to define is half-life. Half-life. So let me put in brackets T half. So this is the time, this is the time taken for a radioactive nuclide to decay to half of its original size. What does that mean? If we have n naught initially, okay, and later we have after some time the number of nuclei present has decayed to n, and this n is half of n naught. You know, we said there is a time taken for radioactive nuclide to decay to half of its original size. So this n is half of n naught. So if you look at our formula, equation 4, we had n equals n naught exponential minus lambda t. So that this n is now n naught over 2, half. So the corresponding time is what we call the half-life. So at the time it takes to decay to half of its original size. So from here, n naught will cancel n naught, so that we have 1 over 2 equals exponential minus lambda t half. Or we can take the reciprocal of both sides, so that we have 2 equals exponential lambda t half. Then we can take the logarithm, take the natural logarithm of both sides. What does that mean? That is, we take the ln of both sides. If we take the ln of both sides, then we have ln 2 equals ln exponential lambda t half. Now, as I stated earlier, if you want, so if you take, earlier I said if you take exponential ln 2, you get 2. If you take exponential ln 8, you get 8. The same thing, if you take ln exponential 2, you still get 2. Ln exponential 20, you get 20, and so on. So ln exponential this, so this is ln 2 equals lambda t half. So that your t half, which is the half-life, will be ln 2 divided by lambda, and lambda is the decay constant. So the relationship between half-life of a radioactive material and decay constant is as given in equation 7. It's as given in equation 7. And from this equation, you can also obtain the expression for decay constant lambda. So if you make lambda the subject of the formula, so you have lambda equals ln 2 over half-life. So that in case you are given half-life and you are asked to calculate the decay constant, so you use this equation. Let's call it 8. Now, what is the SI unit of activity? Okay, units. What are the units of activity? So the unit of activity is decay per second. Decay per second. And in some cases, this decay per second is actually equivalent to becquerel. Okay, becquerel, which is BQ. Okay, so 1 BQ, 1 becquerel means 1 decay per second. 1 decay per second. Then another unit that is often used is Curie. Okay, capital letter C, small letter I, Curie. So the symbol for becquerel is capital letter B, small letter Q. The symbol for Curie is capital letter C, small letter I. So, and this Curie is related to becquerel or decay per second as 3.7 times 10 raised to the power 10 becquerel, or 10 raised to the power 10 decay per second. It's the same thing, because 1 becquerel is 1 decay per second. Decay per second. 1 becquerel is 1 decay per second. So these are the units that you can use for your activity. Now we'll take 2 examples, then we stop. So the first example, I think we've had an example. Okay, example 1. So let me call it example 2. Okay, so example 2. a radioactive isotope. Let me pause the time so as to save the size of the file. Okay, so the example is this. A radioactive isotope has an initial activity of 6 millicurie and 24 hours. So this is the activity at time t equals 0, or at initial time, initial time. So it's 6 millicurie. And 24 hours later, that is when t equals 24, the activity is now 4 millicurie. So the question is, what is the half-life of the isotope? What is the half-life of the isotope? So So we can use our equation, is it 5 or 6? Equation 6. So we can use our equation 6. So let me say using equation 6. So that equation 6 is R equals R naught exponential minus lambda t. So we have to determine the half-life. And we are given R. So we are given R is given. R is given. R naught is given. The time t is also given. So we are asked to calculate the half-life. So to determine the half-life, we can determine that from the decay constant. So we need to determine the decay constant. After the decay constant, we can now use equation 8 to determine equation 7 to determine the half-life. Okay. So R equals R naught exponential minus lambda t. R naught is 6. R naught is 6. So let me say R naught is 6 millicurie, while R is 4 millicurie. That is at initial time, which is R naught. The activity R naught is 6 millicurie. Then at time t, that is R of t, the activity is 4 millicurie. So that this is 4 millicurie equals 6 millicurie exponential minus lambda. T is 24 hours. 24 hours. So millicurie comes to millicurie. So we have 4 over 6. 4 over 6 equals exponential minus lambda 24 hours. So we can convert 24 hours to seconds. Okay, to seconds. We can leave it as 24. Then 4 over 6, that is like 2. That is 2 over 3 equals exponential minus, let's say, 24 lambda. So we know that this 24 is in hours. Then we can write this as 3 over 2 equals exponential 24 lambda. That is, you find the reciprocal of both sides. So here you find the reciprocal of this, then you find the reciprocal of this. When you find the reciprocal of exponential minus 2, it is 1 over this is 1 over exponential 2, and the reciprocal is now what? Exponential 2. Okay, because if you want to find the reciprocal of 1 over exponential minus 2, it's like saying 1 over exponential 2. So that'll be exponential 2. So if you find the reciprocal of this exponential minus 24 lambda, you get exponential 24 lambda. Again, so you take the natural logarithm of both sides. So you have ln 3 over 2 equals ln exponential 24 lambda. So ln exponential, this will lead to 24 lambda. Or you can say your lambda will be ln 3 over 2 divided by 24. So what is ln 3 over 2 divided by 24? Okay, so let's take out the calculator and take ln 3 over 2 divided by 24. So ln 3 over 2, which is 1.5, divided by 24. So ln 3, I wrote 1 divided by 5, 1.5 divided by 24. So that is 0.016 894 89438, and this will be, this 24 is in hours. Okay, don't forget. So this will be per hour. So per hour. So that is the decay constant, and we can definitely convert this to per second. So we divide through by 3,600 seconds, because 60 seconds make 1 minute, 60 minutes is 1 hour. so that 360 times 60, which is 3,600 seconds, is 1 hour. So we divide this value by 3,600 so that we can get the answer in per second. So this divided by 3,600, and that will be 4.693 times 10 to the power minus 6. So 4.693 times 10 to the power minus 6 per second. So that's your decay constant. Then from there you can determine the half-life. So to determine the half-life, we use equation 7. So using equation 7, so we can determine the half-life, which is ln 2 divided by lambda, which is ln 2 divided by 4.693 times 10 to the power minus 6 per second, and that will be, so ln 2 divided by that value. So let's say ln 2 divided by this value. So that will be 1.4, approximately 1.48 times 10 to the power 5. So 1.48 approximately times 10 to the power 5 seconds. So this is the half-life of the isotope. The half-life of the isotope. All right. Now the last example for today. So let's call it example 3. Example 3. Again, let me pause to write the question. Okay. So the question is cobalt 60 is a radioactive isotope commonly used for radiation therapy. It has a half-life of 5.24 years. So the question is, what is the activity of 1 gram of cobalt 60? So solution. So what we do is we start, of course, we want to calculate the activity. So to calculate the activity, so we need the activity. So the activity can be obtained from lambda n, okay, where lambda is the decay constant, and since we are given the half-life, so the half-life they said is 5.24 years, so we can determine activity from half-life. So activity lambda can be obtained using ln 2 over half-life, which is ln 2 over 5.24 years. So we convert this 5.24 years to seconds. That will be 5.24 years multiplied by, how many days do we have in a year? We have 365.25 days. Then how many hours do we have in a day? We have 24 hours. How many seconds do we have in 1 hour? We have 3,600 seconds. Okay, so that decay constant lambda can be obtained as ln 2 divided by, so if you multiply this, let's see, so we have 5.24 multiplied by 365.25 multiplied by 24 multiplied by 3,600. So we have 165,361,824. So 165,361,824. 165,361,824. All right. So that will be second. So if you take the natural logarithm of this, that's the natural logarithm of 2 divided by that value. So we have ln 2 divided by that value. So that will be, I think, so I've changed it to scientific notation so that it will be easier to write. So ln 2 divided by that 165,361,824 gives 4.1917 times 10 to the power minus 9. 4.19 approximately times 10 to the power minus 9 per second. So that's the decay constant. Now, how do we obtain the number of nuclei present? We are told that the mass is 1 gram. So to know the number of nuclei present in 1 gram, we divide by the mass, the molar mass, which is 60 gram per mole. Then we multiply by the Avogadro's constant, which is 6.02 times 10 raised to the power 23. Now this will now give 1 multiplied by 6.0, then divided by 60. So we have 1 multiplied by 6.02 times 10 raised to the power 23 and divided by 60. So that would be 1.003 times 10 raised to the power 22. 1.003 times 10 to the power 22. So that would be the number of nuclei. Now, so therefore, the activity R equals lambda n can now be written as the lambda is 4.19 times 10 to the power what? 10 to the power minus 9 times 10 to the power minus 9 per second, multiplied by the number of nuclei present, which is 1.003 times 10 to the power 22. That's for the 1 gram. In 1 gram. So this will be 4.19. Okay, so just multiply by 4.19 times 10 to the power minus 9. So that is 4.2 times 10 to the power 13. So 4.2 times 10 to the power 13. 4.2 approximately 0 times 10 to the power 13 decay per second or becquerel. So we can use decay per second, or you can write it as 4.2 times 10 to the power 13 becquerel. And you can also use curie. Okay, 1 curie we said is 3.7 times 10 to the power 10. Okay, I think I gave you so 1 curie is 3.7 times 10 to the power 10 becquerel. So to get the answer in curie, so you can divide this value. So in curie, divide by 3.7 times 10 to the power 10. So that R will be the 4.2 that we got, then divide by 3.7 times 10 to the power 10. And that will, it should be multiplied. Multiplied by. I think I made a mistake somewhere. This we got 4 points. Okay, so it should be division. So it's correct. So but you have to put it in brackets. Okay, so 4.2 times 10 to the power 13 divided by 3.7 to the power 10. So that's when you get 1135.1351. So you have activity equals 1135 okay, approximately curie. Okay, but in exam you can leave your answer in becquerel, or if you want to get your answer in curie, you divide by 3.7 times 10 to the power 10. Okay. All right, so this is where we stop today. So see you next week.